Hello and welcome to part 5 of chapter 12. In this last part of our lecture on this chapter, we will be looking at phase changes, heat of transformation, and heat transfer. Let's start with phase changes and heat of transformation. So the three phases of matter that we're going to look at are gas, liquid, and solid. The best way to explain this is with a computer simulation, so let's just go right to the computer simulation. This is a computer simulation that demonstrates the states of matter. So what I've selected here is the atom argon, or the element argon, which is normally a gas at room temperature, but we're going to start here with our argon sample at a very low temperature. You can see that we've got it set to 2 kelvins, which is only 2 degrees above absolute zero. That means that the temperature here is about 460 degrees below 0 Fahrenheit. So at this low temperature, you can see the argon here, which is represented by these little pink spheres here, are the argon atoms. They're all connected together solidly, and so this is the solid phase of argon. So this is argon ice, basically. You can see that there's a little bit of thermal motion. You can see the molecules are wiggling around just a tiny bit, but they are held in place rigidly by the bonds between the atoms, and these atomic bonds are very strong at this temperature. It makes this a solid object. So what we can do here is add some heat to our ice crystal here. So you can see the temperature is now up to 20 kelvins. We still have a solid phase here, but notice now there's some more thermal energy added to our ice crystal, and the little atoms are wiggling around more vigorously now. So now as we keep adding more heat and thermal energy, we see something start to happen. Some of the atoms now have enough energy that they actually break apart from their neighbor. So this is what's happening here, is melting. We're starting to see the solid break apart, and some of the atoms are able to slip and slide. So as I keep adding a little more heat, we're going to enter the liquid phase of the argon. So now you can see that the argon atoms are completely slipping and sliding past each other. There's no more shape to this piece of argon. It's no longer a solid. We have entered the liquid phase. One thing you can also see here is that occasionally one of these atoms gets enough energy to actually get kicked right out of the liquid. And so this is evaporation starting, and this is going to increase as we keep adding more and more temperature. So let's go ahead and raise the temperature more and heat up this liquid argon. So we're seeing more and more activity now by the atoms. So look what's happening now. We've got the argon atoms have so much energy that they don't even stick together at all anymore. They're all flying apart separately. We have now formed argon gas, right? This is the gas phase of the argon. And we can go back. Oh, and let me just keep adding. I'll keep increasing the temperature. As I keep raising the temperature, you can see we're now up to about 280 kelvins. That just means there's more and more motion of these atoms. They're going faster because, remember, that's higher temperature, just means faster motion of the gas atoms. We can go in reverse. Let's you can see me adding the ice down here at the bottom, and we can bring that temperature back down. And let's see what happens here. Notice that now that the atoms are slowing down, some of them are starting to actually stick together a little bit occasionally. And as we lower the temperature, you'll see more and more of them start to stick together. So they don't have enough motion now to break apart from each other, and their attractive forces to each other are starting to cause them to clump together. This is, we're having what's called condensation here. We're going from the gas phase back into the liquid phase. And so now here we have our liquid phase, where the argon atoms are down here and they're basically slipping and sliding around each other. And if I keep lowering the temperature even more, we solidify the liquid. Now notice the atoms are actually bound to each other, and they're not really moving apart anymore. They can't slip and slide past each other. We've formed another argon ice crystal. Whenever we change phase from either a solid to a liquid or a liquid to a gas phase, we have something comes up called the heat of transformation, and this has to do with melting and boiling. So the best way to maybe explain this is showing a little diagram here. So we're going to start down here at the bottom of our diagram, and you can see we've got frozen water ice here. So let's say we start heating up this ice. So we pump some heat into here. So what happens is the ice, which initially starts well below the melting temperature, starts to warm up, but it's still ice. Once we get to the melting temperature of the ice, okay, so if we're talking about water, this happens at 0 degrees Celsius, we are starting to undergo a phase transformation. But a phase transformation requires breaking those bonds from the solid to get into the liquid phase, and this requires energy. So this energy is called the heat of fusion. And the heat of fusion is given the symbol L sub F. And the L stands for latent, which means hidden. All right, and so what is L sub F? Well, it's the heat needed to melt 1 kilogram of a solid. So the idea here is that melting is a phase change that requires additional heat to break the molecular bonds of the solid or liquid. In this case, we're talking about going from a solid to a liquid. So in order for this ice to melt, it's going to have to absorb heat from its surroundings. So once we get enough heat of fusion to melt all this ice, what we've got now is cold water at the same temperature that the ice was. In other words, this heat of fusion does not raise the temperature of the substance. It only changes the phase. Once we reach the state of the ice turning into water, though, now if we keep adding heat, we start warming up the water. So this is this part here where we're warming. And once the water reaches the boiling point up here, another phase change occurs. And this requires the heat of vaporization to actually turn this water into steam or vapor. So the heat of vaporization, which is designated L sub V, is the heat needed to vaporize 1 kilogram of liquid. So once all this heat is pumped in, we've turned this water into steam or vapor or gas, basically, at the same temperature. And by the way, on the Celsius scale, this is 100 degrees Celsius. On the Fahrenheit scale, it's 212 degrees Fahrenheit. But again, this heat that we're adding here to boil the water does not raise the temperature of the water. It's just changing the phase from liquid to gas. And then once we've created steam or water vapor here, now any additional heat we add will heat up and increase the temperature of the steam. So here's an example of a graph that kind of nicely shows what's going on when we start with ice and we eventually turn it into steam. So on the vertical axis here is the temperature, and what we're going to do here is take 1 kilogram of water or ice, start with ice. So that's a liter. Think of a liter bottle of frozen water. And we're going to start at 100 degrees, minus 100 degrees Celsius. So that's 100 degrees below the freezing point of water. And we are going to eventually boil it and turn it into steam and increase the temperature of the steam up to 200 degrees Celsius. So let's look at what this process looks like on a graph with temperature plotted here on the vertical axis versus the heat added down here, and the heat added is given in units of kilojoules. A kilojoule is 1,000 joules. So what happens here is we start at the beginning here at minus 100 degrees Celsius. So we're in the solid ice phase. We start adding heat, and so the ice warms up as we add heat. Once we get to 0 degrees Celsius, we've reached the melting temperature of ice, but the ice doesn't just all of a sudden turn into water at this temperature. Instead, we have to pump in heat called the heat of fusion that melts the ice. So this is a phase change here. And in the heat of fusion, it's listed over here for melting water, is 333,000 joules per kilogram. So since we've got 1 kilogram of water in our sample, we have to add 333,000 joules to get this ice to turn to water. But notice that the temperature has not increased a single degree. All we've done here is melted the ice and turn it into liquid by breaking those bonds. And this takes a lot of energy. That's why we took all this heat, 333,000 joules, in order to break those bonds and melt the ice and turn it into cold water. Once the ice is melted, and we keep adding heat though, now the temperature starts to rise because we don't have to do a phase change. This is liquid. We're in the liquid water phase, and we're moving up like this until we reach the boiling point of water, which is 100 degrees Celsius. Once we reach the boiling point, it takes extra energy now to vaporize the water and boil it, turn it into gas or steam. And if you look here, the latent heat of vaporization, L sub V, is 2,260,000 joules per kilogram. So we have to add all this heat, 2.25 million joules of heat, just to get the water to turn into steam. This is how much energy it takes to break all those bonds in the liquid phase here and free all those water molecules so that they can fly around freely as a gas. So once we finally do that, then any additional heat that we pump into the system will start to raise the temperature of the gas or the steam, which finally ends up here at 200 degrees Celsius. So this plot here has a couple of interesting features in it. First of all, we see that whenever there's a phase change, we see a horizontal portion of the graph here. That just means that we're adding energy, but the temperature is not increasing. All the energy is going into the phase change. The other thing, we notice that this sloped line down here represents the solid phase. This sloped line here represents the liquid phase, and this sloped line up here represents the gas phase. And these temperatures that separate those phases, well, this 100 degrees here is the boiling point, and this temperature here, 0 degrees, is the freezing point. One other comment here, the slopes of these lines basically are the inverse or the reciprocal of the specific heat. So for example, if we look at this section here where we have liquid water, if you take the slope of this line, you're basically getting the amount of, well, the slope is the change in temperature over the heat added. The reciprocal of that slope gives us the specific heat of water, which is 4,190 joules per kilogram per degree Celsius. Likewise, the slopes of these other lines here give us the specific heat for the ice phase and for the steam phase. Notice those are different than the specific heat of the liquid phase. So during the warming parts of the graph, that's where we see these slopes. We use Q equals specific heat times the mass times delta T. This is the relationship we saw earlier in this lecture, in this chapter. And for a phase change, the amount of heat is equal to the heat of transformation, that's L. We use either LF, this heat of fusion for here, or LV, the heat of vaporization up here. We multiply the heat of transformation times the mass of the substance, in this case it would be 1 kilogram, and that tells us the amount of heat needed to do that phase change. So the phase changes of condensation and freezing are sort of the opposite of boiling and melting. So if we take a similar look at, the water example here, and if we start up here at the top, and this is, sort of showing thermal energy going up, let's say we start with steam and we start cooling it off. So in order to cool off the steam, we're going to have to release heat from the steam to the environment. Okay, so this is cooling. We're losing heat in this sense. Once the steam gets down to the boiling point of water, Now what happens is there's a tremendous release of heat, and this is the heat of vaporization that's actually released. So when steam turns into water, this is called condensation. This is actually releasing heat to the environment. Then the water cools down, and it cools down by releasing more heat to the environment. Heat, Q, joules of heat are leaving the water as it cools down. And when the water gets to the freezing point here, which is 0 degrees Celsius, the water will release more heat, and this is again called the heat of fusion. This is this heat of transformation called heat of fusion, and this heat has to be removed from the system so that the water can turn to ice. The surprising thing here is that freezing is a process that actually releases heat to fusion. So the process of freezing gives off heat, which sounds a little bit counterintuitive. Let's now turn to heat transfer. So there are 4 heat transfer mechanisms. They are conduction, convection, radiation, and evaporation. So we're going to look at each of these in some detail, but just kind of real briefly to get an overview of what we're going to do here. Conduction is when we have a hot object placed in contact with a cold object, and heat flows directly by contact from the hot object to the cold object. So this black arrow here represents the transfer of thermal energy, which is heat moving from hot to cold. Convection, which is shown here, is when you have basically warm or hot gases basically transfer heat. And we'll talk about this in more detail a little bit later in this lecture. Radiation is when you have a hot object that actually radiates thermal energy in the form of usually infrared electromagnetic radiation. And we will also look at that briefly a little bit later in the section. Finally, evaporation is the process where you have a liquid and it actually evaporates and turns into a gas. For example, if you have a dish of water on the table and you come back a day later, the water is dried up. And this is a heat transfer mechanism as well, as we'll talk about later. So let's start by talking about heat conduction in some detail. So conduction is heat transfer by direct contact between objects. Heat flows from hot to cold. So imagine you have this cast iron skillet on top of maybe you're camping and you're gonna fry up some fish or something like that, and you set it on the fire like this. Well, obviously, if you grab the handle here, and it's all metal here, you're probably going to burn your hand. So why is that? Well, what happens here, and what they're kind of showing here, is that heat conduction is the transfer of heat from this hot fire through the metal down to your hand on the handle. And the way this works, we can see that here. If you've got a chunk of metal here and you stick one end in the flame, you can see we start heating up these atoms at the end, and they start bumping into the ones next to them, and pretty soon the whole thing is wiggling and jiggling like crazy, which means it's become very hot. So you can see the heat is transferring from the hot end down here, and the thermal energy is actually moving to the right in this picture, just like it moves to the left in this picture here. So there's a formula for the rate of heat transfer for conduction, and it's shown like this. The rate of heat transfer is the amount of heat Q divided by the time. So this is in joules per second, and it's given by this equation here. The key thing here is this parameter K. K is called the thermal conductivity of the material, and different materials have different thermal conductivities. So we usually look those up in a table like this. Metals typically have very high thermal conductivities, and we're not going to get into the reasons for that, but it has to do with the free electrons that can move around inside the metal, and they can conduct heat. Biological materials like skin, muscle, and fat, much lower thermal conductivities. And in fact, if you look at something like fur or feathers, notice the thermal conductivities are really low. This is because they are good at insulating. They're basically insulation. They keep us warm, or they keep animals warm. And so as a result, it's hard to move heat through insulating materials like fur or feathers. So this formula here, the rate is equal to K times A. Now A is the cross-sectional area of the object that is transferring the heat, and L is the length of the object that is transferring the heat. And then delta T, this is what drives the heat transfer. This is the change in temperature, the difference in temperature from the hot end here to the cold end over here. And again, you know, if there's no difference in temperature, you're not going to get any heat flow. If delta T is 0, then the rate of heat transfer will be 0. But for large delta T's, in other words, if you have something really hot on one end and really cold on the other end, that's going to mean a lot of heat is going to flow through this object. So let's look at an example here. So let's say one end of a copper rod and the copper rod has a length of 1 meter and it has a radius of 1 centimeter, is placed in a fire at a temperature of 900 degrees Celsius. So here's our hot end of the copper rod over here. The other end of the rod is placed on ice, which is at 0 degrees Celsius over here. What is the rate of heat flowing through the rod? So you can kind of see what's happening here. The heat is coming from the fire, and remember, you know, inside the rod, all the copper atoms are wiggling and jiggling, and as they start to wiggle and jiggle over here, they start to, you know, affect the neighbors, their neighboring atoms. And so this heat transfer moves along this copper rod, heat, thermal energy flowing from the fire to the ice. So let's plug in some numbers here and figure out the rate of heat flow. Here's the equation from the last slide. We have to figure out the cross-sectional area. So the area of a copper rod here is pi r squared, and remember the radius was given as 1 centimeter or 0.01 meters. So this is the number for the radius that we're going to plug in. The thermal conductivity of copper from our table on the last slide is 400. Okay, so I'll put that in there, and it's 400 watts per meter per Kelvin. We multiply that by the cross-sectional area in square meters, and we divide by the length in meters. And and then delta T, of course, that's our temperature difference between the fire and the ice. Well, the temperature difference is 900 degrees Celsius, but remember that a degree Celsius is the same as a degree Kelvin. So the delta T in absolute temperature, or kelvins, is also 900 Kelvin, 900. So we have 900 kelvins here. So you can see what happens here with the units. This Kelvin down here cancels this Kelvin here. We've got meters squared here, and there's a meter M there and an M here, so these two M's cancel these two M's, and we're left with just the watts. So if we take 400 and multiply it by this number on our calculator, and you know, we don't have to divide by 1, so that doesn't do anything, and then multiply by 900, we end up with an answer of 113 watts. Now remember, a watt is a joule per second. We learned about the watt when we talked about power earlier in the course. So what this tells us is that 113 joules of thermal energy are flowing through this rod every second. Here's an interesting demonstration of conductivity, thermal conductivity, or conduction, that you can do right now at home. Take your hand and place it on, I'm assuming maybe you have a notebook nearby with paper in it. So touch your notebook with the paper, and then also touch the desktop or tabletop, which is, I'm assuming, is wood or something like that, and feel that. And then find a large metal object. For example, the metal leg of a desk or table or chair. You might have to look around the house a little bit for that. Maybe there's some shelves or cabinets or something that has a large amount of metal. Now, if you feel those three objects, which one feels colder? So I'm guessing that you're going to say that the metal object felt cold and the desktop was kind of in the middle, and then the notebook felt warm. Well, the question is there really a temperature difference of those three materials? And the answer is no, they're all at the same temperature because they're all inside your house, and so they're at thermal equilibrium, meaning they're all about 70 degrees. So why does the paper notebook, the wooden desktop, and the metal legs of the table, why do they feel like they're at different temperatures? Well, the reason for this is because of the difference in thermal conductivity of the three materials. Metal has a very high thermal conductivity, so it draws the heat away from your hand very quickly, leaving your hand at a cool temperature, which is equal to the temperature of the metal. On the other hand, the paper up here in your notebook has a very low thermal conductivity. Paper is like a good insulator. So what happens is when you touch it, the heat from your hand doesn't really leave your hand at all. It gets trapped on the paper. So the paper feels like the temperature of your hand. Let's just real briefly talk about convection. Convection is heat transfer by the motion of a fluid. And what we mean by a fluid is anything that flows. So it could be a gas or a liquid. So something you're familiar with is smoke, right? If you see smoke coming from either a cigarette or a campfire or whatever, the smoke always rises. Now why is that? Well, the smoke is higher temperature. It's been heated up. And so when a gas heats up, it expands, and that makes it less dense and makes it lighter. So as a result, it rises, okay? It rises above the cooler air around it. So this is a heat transfer mechanism. This hot gas, which has basically got heat from the fire down here, is rising up and pulling the heat along with it. When you boil a pot on the stove, you have convection. You have heat coming up from the bottom where the flame is, or the heat source, and then as it cools off, that water comes back down. So as a result, there are convection currents inside of the pot of water. This is just an experiment here where they put a warm it's some sort of dye or ink in this container, and they warmed it up and they placed it in a beaker of cold water, and because this fluid is warmer, it's less dense. Remember, it has expanded, and so it will float up to the top, and so you can see a convection current here of the colored material. The next type of heat transfer mechanism we're going to talk about is radiation. So radiation is heat transferred by electromagnetic radiation. And this is something, electromagnetic radiation is really something that we're going to talk about in much more detail in Physics 102. If you do take Physics 102, you'll learn all about EM radiation there. But for now, we're going to talk about the heat transfer mechanism of radiation. So the physics here is that any object warmer than its surroundings will radiate heat as infrared radiation. So whether you're talking about the surface of the sun, sitting out in cold space, that's going to radiate a lot of heat. And that radiant heat obviously travels through space and reaches the Earth and warms our planet. A hot poker stuck in a fire, when you pull it out, right, it's glowing red, and you can imagine just feeling the heat radiating off of the tip of this glowing piece of iron. If we look at the human body, with our eyes, we don't see infrared, okay? Infrared is not in the visible part of the spectrum. So infrared is invisible to our eyes, but if we were to look at a human body with an infrared camera and do some infrared imaging, we would see that our body glows, and our bodies are giving off infrared radiation. So is the little dog here. So let's take a look at the mathematics of radiative heat transfer. It turns out that an object both emits and absorbs heat from its surroundings at the same time. So the amount of heat emitted, this is the rate of heat emitted. So remember, Q is for heat. So Q emitted over delta T is given by, this is sometimes called the Stefan-Boltzmann law. This equation here tells us the rate of heat emission by radiation. So it's got a bunch of terms in here. This first term, E, is called the emissivity of the object. It's how well the object radiates and absorbs. And emissivity is a number between 0 and 1, and this is something that would typically be looked up or given to you in the problem. This next symbol is sigma. And this is the so-called Stefan-Boltzmann constant. Sigma is just a number that we plug into the equation. It's 5.67 times 10 to the minus 8. A is the surface area of the object in square meters, okay? And T is the temperature of the object in kelvins. So these two, E and sigma, are both constants. So you can see that the rate of heat emitted really depends on two things: how big the object is and how hot the object is. Larger objects give off more heat because there's just more surface area that can radiate, and hotter objects obviously are going to give off more heat. Now notice T is raised to the 4th power. So the amount of thermal emission by radiation is a strong function of temperature. Just slight temperature increases can change the amount of heat emitted by quite a bit. Now there's a similar equation right over here for the rate of heat absorbed from the surroundings. And notice it's the same equation. The only difference here is the temperature here is T naught to the 4th power. And T naught is the temperature of the surroundings. So that is like the ambient surrounding temperature. And again, temperature in these equations is always in kelvins. So the net rate of heat either emitted or absorbed is just the difference between these, because one of these gives off heat and the other equation is how much heat you absorb. So the amount emitted, rate emitted minus rate absorbed, is just this equation over here minus this equation up here. And notice, since the same parameters, E, sigma, and A, appear in both equations, let's go ahead and factor those out, and we end up with this result here, which tells us the net rate of heat gained or lost to the surroundings. So again, we have to know the emissivity, we have to know the Stefan-Boltzmann constant, we have to know the surface area of the object, and these are the two temperatures. T is the temperature of the object, T naught is the temperature of the surroundings. Let's do an example that uses radiative cooling and emissivity. This is a little bit of home economics here. What's the best way to keep baked potatoes warm before we serve them? So, we take the potatoes out of the oven. Should we leave them, just kind of bare like this, or should we wrap them in foil? You could argue maybe the foil is going to help, although maybe the foil will conduct heat away from the potato and it'll actually cool faster. So what's the best way to keep our hot potatoes hot? Well, let's take a look at this from the standpoint of rate of cooling. So if we just look at the heat emitted equation, so the rate of heat emitted, remember, is emissivity times sigma times the surface area times the temperature. Let's do a little math here. So the surface area of a typical potato is approximately 0.03 square meters. All right, I had to do a little research here and a little bit of calculating to get that number. Typical temperature of an oven to bake a potato, 350 Fahrenheit. Well, that's 450 kelvins. Now, here's the key difference. So this potato here on the left side has these numbers, this area and this temperature. If we wrap the potato in foil, well, it still has the same area and it still has the same temperature, right? It came out of the same oven, so it's still 350 degrees or 450 kelvins. But the big difference is the emissivity. A bare potato, in other words, the potato skin on the outside, has an emissivity of 0.9. Aluminum foil, especially the shiny side of it, has a very low emissivity of 0.04. So if we plug in these numbers here, the only difference is the emissivity. The cooling rate here is 63 joules per second. The cooling rate over here with the foil is only 3 joules per second. What's the difference? It's the foil has a much lower emissivity. It doesn't emit heat nearly as fast as the potato skin here. In fact, it's about almost 20 times less heat loss because of that shiny surface has a lower emissivity. Okay, so let's move on from here. This is, by the way, this is kind of making me hungry for some baked potatoes. Here's sort of an interesting example where we can use this. Again, it's a little more interesting maybe than the baked potato problem. This is the net rate of cooling of the human body. So let's take a person that has a skin temperature of 91 degrees Fahrenheit. Now remember, the inside of our body is 98.6 Fahrenheit, but our skin is never that warm unless we've been exercising or, you know, laying out in the sun or something like that. So typical skin temperature we'll take as 91 degrees Fahrenheit, which is 33 degrees Celsius. And let's say this person is in a room that is at a temperature of 75 degrees Fahrenheit, which I converted is 24 degrees Celsius. The surface area of a typical person is about 1.8 square meters. The emissivity of human skin is actually very high. It's almost 1. Remember, the highest emissivity can be is 1. So it's 0.97. What is the net rate of heat loss? Okay, so here's our formula. Remember, we have to take into account both the temperature of the object, which is the human, and the temperature of the surroundings, all right, the environment, which is T0. So let's plug in our numbers. E is emissivity, 0.97. Sigma is the Stefan-Boltzmann constant, which is right here. A is the surface area of the human in square meters. That was given at 1.8. And then T to the 4th. So the temperature of a human, remember, we're talking about the skin temperature here. The surface temperature was 33 Celsius. If we add 273 to that to convert it to kelvins, we get 306. And remember, that has to be raised to the 4th power. The room is at 24 Celsius. Convert that to kelvins by adding 273, and you get 297. And remember, that also has to be raised to the 4th power. So this whole string of numbers here multiplied together, you know, do this first in the parentheses, will give you a net heat loss of 98 watts. That's 98 joules per second. So think about this answer. This is consistent with what we learned back in chapter 11. The resting human body metabolism is about 100 watts, right? We got very close to that, 98 watts. You must burn 100 joules per second, which, by the way, that's 0.02 calories per second, or 86 calories per hour, or around 2,000 calories per day, just to maintain body temperature. This is the high price of being warm-blooded. So, you know, having warm bodies, it has its advantages for survival and so forth, but it comes at a price. We have to consume 2,000 food calories a day just to replace all of the thermal energy that is radiating away from our body because our body is warmer than its surroundings. Okay, the last type of heat transfer mechanism that we're looking at here is evaporation. Evaporation is a process where a liquid turns to vapor at temperatures below the boiling temperature. So in other words, you take a little dish of water and leave it out. Now the water is at room temperature, okay? It's nowhere near its boiling temperature, but over time that water will all evaporate and it'll be gone. So how does this happen? Well, it turns out that evaporation, first of all, it's a cooling process, and the reason for this is the remaining liquid is cooled down because only the fastest molecules can leave the liquid. So think about, here we've got the water here. Remember, the motion of the water molecules is random. Some are going slow, some are going really fast. Now, if a really fast moving water molecule gets to the surface of the water, it may have enough speed to actually break away from the liquid below and become vapor. So this is happening constantly. This is, when you take a shower and you get out of the shower and you towel off, you're still damp, but within a couple minutes, you're completely dry. All of that water has evaporated from your body. Now, this is a cooling process because think about which molecules are leaving the liquid. It's the ones that were moving the fastest. So this is sort of a selection process. What's left behind is water with molecules that are moving slower than at the initial start. So what happens here is this is lowering the average kinetic energy of the remaining molecules, and this therefore lowers the temperature of the water. So evaporation is a cooling process. It cools down the object from which the water is evaporating from. So evaporation then is a heat transfer mechanism, and we said, it's a mechanism of cooling, and it's a very important cooling process for animals to regulate their temperatures. So perspiration, sweat, removes excess heat from the body. So when water boils, which boils at 100 degrees Celsius, the heat of vaporization is given by L sub V, which we said was 22.6 times 10 to the 5th joules per kilogram. However, we're not talking about boiling here. We're talking about water evaporating at room temperature or body temperature. So when sweat evaporates at body temperature, the heat of vaporization is actually 24 times 10 to the 5th joules per kilogram. Now, remember, 1 liter of water is 1 kilogram. So the amount of heat that is released or taken away from your body when you sweat 1 liter of water, we can calculate that very easily by taking the heat of vaporization here, 24 times 10 to the 5th, and multiplying it by 1 kilogram, which is 1 liter of water here. And what we end up with is, this number basically. It's 24 times 10 to the 5th. That's 2.4 million joules. So if you drink and sweat out 1 liter of water during, for example, a run, an exercise session, let's say maybe you're hiking in the desert when it's really hot, it's very easy to drink a liter of water over, say, the course of an hour. You are actually removing 2.4 million joules of excess heat from your body, which will obviously help you stay cool and safe. Okay, that is the end of this long chapter 12. We had 5 parts. It was quite a grind to get through this chapter. We will continue on with chapter 13 next.